Sometimes we need to use our knowledge of matrix multiplication and solving matrix equations to sort of solve worded problems using matrices. Some of the questions in exercise 10E towards the end are definitely worth having a go at. So one of the questions I've just taken from the exercise is this one with Brad, Flynn and Lena, and the matrix shows the number of dresses, shirts and pants each one of those people produces per week. It tells us in the question that the warehouse requires 300 dresses, 175 pants and 175 shirts at the end of a week. And so how many contractors should each employer employ to meet that requirement exactly? So we can use matrices to do that. And you can see here I have made a matrix, column matrix, with X, Y and Z in it. So it's an unknown matrix at this point. The matrix that the question gave is listed there, and the answer matrix is given there also. So the one that I need to figure out is the column matrix that I've called X, Y, Z. So if X, that unknown there, represents the number of employees required by Brad, Y is the number required by Flynn, and Z is the number required by Lena. If I can solve that matrix equation and find out what X, Y and Z is, then obviously I already know now how many employees are required by Brad, Flynn and Lena. So if we imagine this matrix, the one they gave us, if we imagine that was matrix A, and the unknown matrix I'm going to call matrix X, and the answer matrix I'm just going to call it C. No particular reason why I've called any of them anything, just that it now looks, if I have an equation, matrix A multiplied by matrix X is equal to matrix C, it now looks like any other matrix equation that I have already solved previously. So the idea is to try and get matrix X isolated on its own, and obviously we know we can't divide with matrices, but we can multiply by an inverse. So if I pre-multiplied by the inverse of matrix A on both sides of that equation, I'll effectively cancel out matrix A on the left-hand side, and I'll be left with matrix X, which is what I want to happen. So to put that into writing, I'll just put it on the side here. Inverse of matrix A pre-multiplied by matrix A and matrix X is equal to pre-multiplying by the inverse of matrix A by matrix C. So this is no different to what we've done previously. This effectively cancels, not really, but cancels that to the identity matrix, and the identity matrix multiplied by matrix X is just X. So that's the reason why I'm doing that, to try and isolate matrix X. So now if I multiplied matrix A inverse by matrix C, I'll end up having a value for matrix X. So if I do that on my calculator, I've already typed in the matrix, so it makes it a little bit easier and quicker. So matrix A is listed there, power -1 to get the inverse, and then multiplied by the answer matrix. And when I do that calculation, my matrix X becomes 20, 10, 15. So little x is equal to 20, little y is equal to 10, little z is equal to 15. So if I solve it, 20, 10 and 15 is what I get for matrix X. So then I can actually answer the question. So in the start of this question, I let X be the number of employees required by Brad. I let Y be the number of employees required by Flynn, etc., etc. So you can see there from those two equivalent matrices, X is 20, Y is 10, Z is 15, So I can actually then answer the question, and the question was how many employees required or how many contractors required by each person, and I can then answer the question. Number of employees required by Brad is 20, number required by Flynn is 10, number required by Lena is 15. So that's the sort of question that we can formulate to get you to use matrix equations in a slightly different way to what you might have done already. So I do encourage you to have a go at exercise 10E, particularly the questions around question 9, question 10, question 11. Those sort of style of question are definitely worth having a look at, because there's none like that in your notes booklet, but they definitely could be exam questions of that style. Definitely worth having a go at.